Alright, we're going to solve two-dimensional force problems. To start off, just a reminder of some right triangle trig. If you have a right triangle, you know sine theta is opposite over hypotenuse, cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. If you need a refresher on that, please see me as soon as possible. Alright, here are the steps, the problem-solving steps for solving a problem where we have two forces in two dimensions. First, you're going to establish your system and draw a free body diagram. When you establish your system, you can either circle the system in a picture, or you can make a list. Then you need to establish positive x direction and positive y direction. That's important to do because a force is a vector. Then you need to break the vectors into components if necessary. So if those forces are not directly up, down, left, or right, then you'll need to break them into components. So for example, that one you would break into Fy and Fx. Then you write a net force equation for the x direction and a net force equation for the y direction. Then you set that net force equal to mass times acceleration, which is Newton's second law, and you solve for any unknowns. So here's a quick little example that I have drawn out. If we have some sort of object and the force of gravity acts down on it, there's a tension force acting to the left and an applied force acting to the right and up. I draw a little diagram of my forces. I've set my positive direction as up and to the right. I have to split my applied force into components. So my x component is calculated here. That's the force applied times the cosine of theta. And then my y component is here, which is the force applied times the sine of theta. So when I write my net force equation in the x direction, I'm just going to add all my forces in the x direction. And we're going to write these net force equations with the vectors. So you're writing them with vectors, which means that you're just adding all of the vectors together. Some of the values will be negative, but you're just adding them together. So in the x direction, we have force applied in the x plus force of tension. And then in the y direction, you have force applied in the y plus force of gravity. Now notice that gravity and tension are acting in the negative direction. So they are going to be negative values. So when you plug in numbers to solve, you would plug in a negative number for force of gravity, and you'd plug in a negative number for force of tension. And then you could solve for whatever you were looking for. So let's try a problem here. We have Tyrone, the turkey, and he's trying to steal a gigantic kernel of corn from Sally the squirrel. The mass of the corn is 0.4 kilograms, excuse me. And he's going to tie a rope around the corn kernel. Here's the corn kernel. That's going to be my system. And pull on that rope with a force of 2 newtons at an angle of 25 degrees with the horizontal. So this angle right here is 25 degrees. And the kernel moves at a constant speed. What is the force of friction on the kernel? What is the normal force on the kernel? So we're looking for force of friction, and we're looking for normal force. So first I establish my system, which is the kernel of corn. And then I'm going to draw my force diagram. So I have my force of gravity acting down. Now, when you're doing quantitative problems, I'm going to let you take off the feeler-dealer part, because otherwise it just gets a little too much. So you just have to write the type of force. Then we know that we have this tension force here, force of tension, and that's got to be split up into Fty and Ftx, and we know this is 25 degrees. And then we also know that there's a frictional force. Now, it says that it moves with a constant speed. So that's important because if it moves at a constant speed, then we know that we're going to have balanced forces. So all the forces to the left equal all the forces to the right, all the forces up equal all the forces down. So the sum of the forces is always 0 in the x and y direction when we're moving at a constant speed. Then, so that means that when I draw my force of friction arrow, I should draw it the same length as this x component of tension. And then I have a normal force acting up on the kernel, and I should draw it so that about the length of the normal force plus the length of the FTY equals force of gravity. It should be pretty close there. Next thing I do is I write my net force equations. So sum of forces in the x direction is equal to force of tension in the x plus force of friction. I forgot to set my positive directions. I'm going to choose to the right and up as positive. And then my sum of my forces in the y direction is equal to normal force plus force of tension in the y plus force of gravity. Now, since my constant speed is 0, I'm going to set my net force equations equal to 0. Really, the step is to set them equal to mass times acceleration. But since my acceleration is 0, that's going to make my net force 0. So I will set those equal to 0. I'm going to kind of jot off to the side here and figure out what the values of my tension in the x and y direction are. So FTY is going to be equal to FT times the sine of 25 degrees. So my force of tension is 2 times the sine of 25. Oh my gosh. And that is 0.85 newtons. And then my FTX is equal to force of tension times the cosine of 25. So that is 2 times the cosine of 25, which is 1.81 newtons. All right, so now I believe I'm ready to start plugging in numbers. So I have my 0 to plug in here, and then my FTX is going to be 1.81, and then that is plus force of friction. So now I solve for my force of friction, and I can see that my force of friction is equal to negative 1.81 newtons. All right, and then I'm going to do the y direction, same thing. So 0 is equal to my normal force, which is what I'm solving for, plus my force of tension in the y direction, which is positive 0.85 newtons, plus my force of gravity. My force of gravity is a negative value. I should also solve for my force of gravity over here. So force of gravity is mass times gravitational field strength. So that's 0.4 kilograms times 9.8 newtons per kilogram, which is going to give me 30. I can do this in my head. I did it in my head before I even typed it in the calculator. 39.2 newtons, and that's a negative value. So because it's acting in my negative direction, so I have to plug in a negative 39.2 newtons there. Doop, doop. Okay, so now I'm just solving for my normal force. So normal force, I'm just gonna add my 39.2 and then subtract 0.85 newtons. And then I get my normal force is equal to, this is wrong, 0.4, haha, not 4. So it's 3.92, not 39.2. I was like, this is not making sense. 3.92, not 39.2. I typed in 4 in my calculator. This is why it makes sense just to use mental math instead of a calculator. Okay, so then 3.92 minus 0.85 is going to give us 3.07 newtons as my normal force. and that's positive. So then we can kind of double check ourselves. My frictional force should be acting in the negative direction, so I should have gotten a negative value in my math. My normal force should be acting in the positive direction, so I should have gotten a positive value. And we can see that normal force plus my force tension in the x direction is equal to my force of tension in the y direction. Normal force plus force of tension in the y is equal to my force of gravity, and so all my forces are balanced. All right, let's do one more. My next one here is two boxes that are connected by a string. The 5 kilogram box is pulled to the right by a force of 40 newtons, so this is my 40 Newton force. And there is no friction between the boxes and the surface. Find the acceleration of the system and the tension in the rope connecting the two boxes. So I have to find acceleration and force of tension. So the first thing I'm going to do is find acceleration, because I think that's the easiest to do first. So I'm going to set my system as this whole thing from my system. I'm going to put both of these masses in my system. It's not going to matter that they're two different masses. All that matters is this amount of mass is being accelerated by this force. So I would draw my force diagram, and I would have force of gravity acting down, normal force acting up, and then my force applied. It's just a force to the right. So these are going to cancel out, and they don't affect the problem, so I'm not even going to write a net force equation for the y direction. I'm just going to focus on the x direction. So sum of the forces in the x direction is just equal to the force. And then I replace my sum of forces with mass times acceleration. And then I'm solving for acceleration. So acceleration is equal to force divided by mass. So my force is 40 newtons, and my mass, my total mass is 25 kilograms, my mass of my system. So then I can do 1.6 as my acceleration. And easy as that. The next piece is to find the tension in the rope. So if I want to find the tension in the rope, now I have to change my system, because right now the way I have it set up, the rope is in the system, and we know that forces within the system can't affect the motion of the system. So this tension force won't be in any equations. So what I'm going to do is change my system, and for the second part, I'm just going to make this 20 kilogram mass of the system. You could also do it with the 5 kilogram mass, but we're going to do it with 20 kilogram mass. And then since the 20 kilogram mass is the system, I'm going to do force of gravity, normal force, acting up, and then there's this force of tension to the right. So these are equal and balanced and don't affect the problem at all, so I'm not even going to write a net force equation in that direction. So some of the forces in the x direction is just, oops, I put normal, this is force of tension. Force of tension, and this is equal to mass times acceleration equals force of tension. We're solving for the force of tension here, so we just plug in our numbers. Force of tension equals the mass. The mass of the system here is 20 kilograms. Times the acceleration of the system, which I solved for in the previous problem, which is 1.6 meters per second squared. And so now we know that our force of tension is equal to 32 newtons. And I know my unit there is newtons because if I look at my units here, I get kilograms times meters per second squared. And that's what a newton is, a kilogram times meter per second squared. You really need to know that, so definitely memorize that. To help you memorize it, you can think of the equation F equals ma, right? So F equals ma, so the units of mass are kilograms, the units of acceleration are meters per second squared, the units of force are newtons. Okay, I'm gonna do it the other way for you, just to show you that you can do it. So let's do our system as just the 5 kilogram block. I think I'm gonna get a darker pen. I don't know if you can see that light green very well. So let's just make the system the 5 kilogram block. So now I have my force of gravity my normal force, my force applied, and then that's just the force, right? And then the force of tension acting back. And this should show unbalanced forces since the 5 kilogram block is accelerating to the right. Now, once again, these are equal and opposite, so they cancel out and we don't have to worry about them. And I write my sum of my forces in the x direction is equal to the force minus the force of tension. So now my sum of forces in the x direction is going to be mass times acceleration is equal to the force minus the force of tension. And I'm solving for the force of tension here, so I'm going to add the force of tension to this side and then subtract ma. So we get force of tension equals force minus ma. And then I just plug in numbers. We get 40 newtons minus the mass 5 kilograms times the acceleration 1.6 meters per second squared, and that should give us, just to show you, minus 5 times 1.6, 32. We get the same thing. So you can do this problem either way. You can set your system as just this or this, but what's important though is that you are establishing your system and making clear what your system is, and then keeping that throughout the whole part of the problem. Have fun solving problems.